Okay, we are ready for Notes 8. This is representing linear non-proportional relationships. A real quick review, proportional relationships start at 0, 0, and so when they are graphed, they are going to start at the 0, 0 and then be linear from there. Non-proportional, we're going to find out. It's probably still going to be linear, but it may not go through the 0, 0, the origin. It may go from somewhere else on the y-axis. So we'll figure all that out. Let's take a look at the first part. It says representing linear relationships using tables. You can use an equation to describe the relationship between two quantities in a real-world situation. You can use a table to show some values that make the equation true. Remember that a proportional relationship is a relationship between two quantities in which the ratio of one quantity to the other is constant. That's what's going to give it our straight line. And then the graph of the proportional relationship is a line that goes through the, and then this should just say origin. So you can take off that little a. The origin means the coordinate point 0, 0. Relationships can have a constant rate of change, but not be proportional. So again, it can still have a constant rate, it can still be a straight line, but not necessarily go through the origin, which is what it means to be proportional. Let's look at this example. The entrance fee for Mountain World, you like the extra capital H there and the large O there, that's okay. The entrance fee for Mountain World theme park is $20. Visitors purchase additional $2 tickets for rides, games, and food. The equation y equals 2x plus 20 gives the total cost, which will be y, so however much we end up spending total is going to be what it equals to over here, your y, to visit the park, including purchasing x number of tickets. So this is going to be how many tickets you buy. So your entire cost is going to be based on the $20 to get in, plus however many $2 tickets you buy, and that will equal our total cost. Okay, let's complete the table. For a number of tickets, if we buy 0 tickets, you're still going to have to be charged to get in. So it's still going to cost you $20 to get in, just if you want to walk around and look. If we bought 2 tickets, let's see. So remember, 2 is our x value, so we're going to go up here to x and we're going to plug in 2. 2 times 2 is 4, plus you have the $20 it costs just to get in. So that would be 24. Now let's change our x value to 4. 4 times 2 is 8, plus the $20 to get in for a total of 28. And then we're going to do it for 6. 6 times 2 is 12, plus 20 is 32. And then lastly, we're going to do it for 8. So 8 times 2 is 16, plus 20, which is 36. All right, and again, our y was our total cost spent, depending on how many tickets we bought. Now we're going to plot these ordered pairs from the table. So again, all you have to do to plot the ordered pairs is take one of our x and y values and turn it into a coordinate point. So 0, 20. So at buying 0 tickets, it still cost you $20 to get in. So put that dot on the y-axis. If we bought 2 tickets, it would have cost us a total of $24 that day. So go over to 2 tickets and $24. 4 tickets, 28. 6 tickets, 32. 8 tickets, 36. Okay, get some type of straight edge, or you can just kind of eyeball it like I'm going to do. Be sure to put an arrow on the end, and again, that represents the fact that we could have bought 10 tickets or 15 or 20. It would have kept going, depending on how much graph paper I gave you. So let's take a look. It is a straight line, and so we're going to describe the shape of the graph. It is going to be a straight line. And another word for a straight line is linear. It's a linear graph. Now let's find the rate of change between each point and the next. So basically what we want to look at is, just like we've done before, from here to here, over from here to here. So from our y's that go on top, 20 to 24, that is a change of 4 per x, which is a change of 2. So 4 per 2, and remember, you flip it We've learned that in lots of other videos. You always put your y's on top over your x's. So my y's over my x's, my rise over my run. So 4 per 2. From here to here, it's another 4 per 2. From here to here, it's another 4 per 2. And then from here to here, it's another 4 per 2. So 4 per 2 equals, and we can simplify that, 2 to 1, or even just, we can even call it 2. But since it's asking us for a rate of change, $2 per ticket. So is the rate constant? The answer is yes. The rate is constant because it's a change of 2 per every one, $2 per every one additional ticket that we buy. Okay, part D says calculate the y per x for the values in the table, and we actually just did that right up here, so we kind of answered part of that. But we're going to look at it now and explain why the relationship between the number of tickets and the total cost is not proportional. So again, proportional means it's going to go through the origin. So why is it not proportional? Why did our graph over here not go down here and start at the origin? Think about it. The reason is because it was not free to get into this Mountain World theme park. It cost us $20 just to get in. So we had already paid money before we even rode any rides. And then depending on how many tickets we bought from there, it went up. So even though the rate is constant, it is not a proportional rate, meaning it doesn't begin at the 0, 0. So go ahead and let's explain that. You can say it costs $20 to get in. That is the actual real world reason that it's not proportional, but according to the graph, the thing that would make it proportional is it would go through the origin, so let's put that too. Our graph does not go through the origin. Okay, it's already time for your turn. So Frank makes $12 per hour doing part-time work on Saturdays. He spends $4 on transportation to and from work. And here's your equation. Y equals 12x minus 4. It gives his earnings Y, so that's how much he total makes, the Y. After transportation costs, and the cost must be he subtracts 4 because he has to pay for transportation, but then he works X number of hours, so $12 per the number of hours worked. Let's make a table for the values in this situation. If you can go ahead and do it on your own, push pause now and try it, and turn it back on when you're ready to check. Okay, let's check. I started with number of hours worked at just 1, 2, 3, and 4. So if he only worked 1 hour, he'd make that 1 times 12, $12 per hour, minus the $4 it's going to cost him to get to and from work, his transportation. So 12 times 1 is 12, minus 4 would have been 8. So he would have earned $8. Even though technically he earned 12, he had to pay for transportation, which would have made his total earnings only $8. After 2 hours worth of work, 24 minus 4 is 20. 3 times 12, which is $36, minus 4 would be 32. And then if he worked 4 hours, 4 times 12 is 48, minus the $4 transportation is 44. Okay, on the next page of your notes, we are looking at representing linear relationships using graphs. A linear equation, and again, that was highlighted before it got copied in black and white. A linear equation is an equation whose ordered pairs form a line when graphed on a coordinate plane. Linear equations can be written in the form y equals mx plus b. I told you a couple of videos ago that this was going to be a very familiar equation, and you guys really kind of need to get used to that. And b does not equal 0, so this will it will not equal 0 in our non-proportional relationships. B would be 0 if this was a proportional relationship, but we are actually going to start somewhere on the y-axis. Like in our previous example, we started at $20 because that's what it costs to get into the theme park. But b is not going to equal 0 in these situations because it's not proportional. And the relationship between x and y, like I just said, is non-proportional. So let's look at the first example. Oh, and you know what, by the way, let me go back to this for a quick sec. I hope you guys remember what m represents. If you forgot, that's going to be the slope. So whenever you see the steepness of your graph, the slope of your line, that number is going to be represented, and that's going to be the slope. All right, now let's look at our example. The diameter of a Douglas fir tree is currently 10 inches when measured at chest height. Over the next 50 years, the diameter is expected to increase by an average growth rate of 2/5 inches per year. So 2/5 of an inch per year. The equation y equals 2/5 x plus 10, which is where it currently is, gives y, which is going to be the total diameter of the tree in inches after x number of years. So x is going to represent whatever number of years we're talking. We're going to draw a graph of the equation and describe the relationship. So first, before we can draw a graph, we have to have some coordinates to put on this graph. So we're going to make a table, and we're going to choose several values of x that make sense in the context. To make calculations easier, choose multiples of 5. Okay, let's talk about that. In the previous example, I just chose 1, 2, 3, 4, and that worked great because I was talking about number of hours worked. But in this example, if I choose 1, 2, 3, 4, I'm going to be multiplying 1 and 2 and 3 and 4 times 2/5. And we're going to get really ugly numbers that have decimals and fractions, and those are going to make our lives a lot more difficult. So if I choose multiples of 5, each of these y values are going to come out even, which is going to make our lives a lot easier. So since we're going to choose multiples of 5, let's start with 0. See where we're at 0 years. Then we'll go 5, 10, 15. Okay, let's calculate this diameter of the tree. Okay, diameter in inches at 0. So go back up here to your x and make your x 0. This is where I'm getting the information. If x is 0, what would y be? So if x is 0, that is 0 times 2/5, which 0 times anything is just 0, plus 10. That's going to equal 10. So our y would equal 10 when x is 0. All right, let's try 5. 5 times 2/5. Another word for multiplying is using the word of. So 2/5 of 5 would just be 2. Or you can take your calculator and multiply it if you're not sure what 2/5 of 5 is. But it's 2 plus 10 is 12. All right, let's plug in 10. 2/5 of 10 is going to be 4, or you can use your calculator. 2/5 times 10 is 4. Plus 10 will be 14. And then 15, 2/5 of 15 is going to be, excuse me, 6. Plus 10 is going to be 16. And again, actually, after you get the first couple, you can just look at kind of what our pattern is. If I went up by 5s every time, and if my choosing of x coordinates was constant, then my y's are going to come out constant too. So if it went from 10 to 12 to 14, I could have just guessed that this is going to be 16 because it's going up by 2s. All right, part B. Let's plot the ordered pairs, the coordinates from the table. So our first coordinate is at 0, 10. So at 0, it was already at 10. This graph isn't in particular going to really be great for our example because our next coordinate is 5, 12. And so if we went over here to 5, it's going to be off the graph just a little bit at 12. But that's okay. You know what? Let's just squeeze one more on there. 10, 14. If we went over to 10, it would be 14. I know it's off the graph, but that's okay. This is, sometimes they don't work out to the best, but that's okay. All right, and we are going to draw as straight of a line as possible with an arrow at the end showing that, we could have kept going and chosen 20, 25, 30, and so on, and it would have been just off the graph even more. All right, draw a line connecting the points to represent all the possible solutions. Okay, by the way, this is talking about a tree, so we could have chosen any of these points within here. Our tree is still growing in diameter. It's just a little bit easier to choose numbers that are of 5 multiples of 5 because that's what made our points even. If we would have chosen like 3, for example, it would have been somewhere in between 10 and 12, but it would have been a fractional number. And just to show that that's correct, if we went to 3 on our graph, it would be somewhere like over 11, maybe 11 and a third or something. I mean, you'd have to work it out. So, but it continues. There's infinite points on these lines, but we just chose a few to represent the height of the tree. All right, letter C. The graph is a line, but it does not go through the origin. Notice this is the origin, the 0, 0 coordinate. It does not go through the origin. So the line is non-proportional, which means it does not go through the origin, but it is actually linear, which means it is a straight line. It is constant. So it can still be constant even though it's non-proportional, meaning it doesn't go through the origin. It's still a straight line. All right, you may pause the video now and try the your turn. I didn't give you a situation. I just want you to use this equation, y equals negative 2x plus 1, and try to plug in the numbers for the table of what the y values would be, and then graph it, straight line, arrows on both ends. Give it a try. Okay, hopefully you guys feel pretty confident on this by now, so I'm going to go kind of quickly. Negative 1 is your x. Negative 1 times negative 2 is positive 2. Plus 1 is 3. 0 times anything is 0. Plus 1 is 1. 1 times negative 2 is just negative 2. Plus 1 is negative 1. And then 2 times negative 2 is negative 4. Plus 1 is negative 3. So these should have been your y values for these particular x values, and then you just turn them into coordinates and graph it. So our first point is at negative 1 comma 3. So go left negative 1 and up 3. 0, 1 is the next coordinate, so at 0, up 1. 1, negative 1 is to the right 1, down 1. And then 2, negative 3 is right 2, down 3. All right. Line through the points, arrows on both ends, showing that we could have chosen any coordinates that would have worked for this particular equation and it would have kept going somewhere on our line. All right, hopefully you did that right. Good job.